Okay, this is chapter 8.3, hypothesis tests in detail. So a couple of key points about a one proportion hypothesis test. It's a procedure for choosing between two hypotheses about the true value of a single population proportion. The test statistic is Z observed, and that's equal to p hat minus your hypothesized value over the standard error. And this test statistic compares the sample proportion to the hypothesized population proportion. Large values of the test statistic tend to discredit the null hypothesis. The standard error is SE equal to, and notice inside this formula we're using P naught, or P with subscript of 0, right, the hypothesized value or the null hypothesized value. It gives us a way of making a decision about the population parameter based on our estimate from a sample, which is uncertain, while knowing the probability that we will incorrectly reject the null hypothesis. This testing procedure only works if the sample size is large enough and the sample is randomly selected. Small p-values indicate an extreme test statistic. An extreme test statistic means something unusual or unexpected has happened. Remember, the smaller the p-value you have, the more evidence you have to reject the null hypothesis. So in the following diagram, which is from page 373 of your text, this illustrates this last point. So we're taking a look at this point again, using a sample of 20 coin tosses to test whether coin is fair. So in this case, if we're testing whether coin is fair, our null hypothesis would be that. So our null hypothesis would be that P is equal to 0.5. In other words, half your tosses end up heads, half end up tails. And our alternative would be that it's not fair, that you don't have half of your coin tosses being heads. All right, so if we look at some examples, this first one, if we get 4 heads out of 20, then our p hat, our sample result, is 0.2. And so our p-value, very tiny. We're looking at the amount of area to the left of this and its counterpart over here on the right. It's a very tiny p-value, telling us that that's probably not going to happen, or it's very extreme, very rare to happen if the die is, if the coin is fair. Right over here, 5 heads out of 20 gives you a p hat equal to 0.25. We're a little closer to the center of the distribution. And so the area that's to the left of that and its counterpart over here is where our p-value comes in. So it's giving us a chance that we get something that extreme or more extreme. So still a pretty tiny p-value, suggesting that's a somewhat extreme outcome. And over here, 6 heads out of 20, a little less extreme. In this case, our p hat is 0.3. So we've got this area and its counterpart here has a total area of about 7% or 7.36%. And if we keep going, notice that the more heads we get, so 7 heads, 8 heads, 9 heads, we'll go up to 10 heads. There's a p hat value of half or 0.5. Notice that p-value is 1. That's definitely likely to happen if you've got a fair coin in front of you. If we keep going, 11 heads. This is a p hat of 0.55. And very close to the middle, something that can happen with a lot of frequency or very likely to happen. So that p-value again is giving us the area to the right of that and its counterpart on the other side. So we would double what we get from our chart. P-value is so big, we don't have any evidence to suggest the coin is not fair. And last one here, just for one more example, our p hat is 12 out of 20 or 0.6. And that's a lot of evidence. I should say that's not a lot of evidence to reject the null hypothesis. There's not enough evidence to say the coin is not fair with that outcome. Okay, so remember that last bullet at the top said small p-values indicate an extreme test statistic. Again, an extreme test statistic means something unusual or unexpected has happened. So up on these top 3, these are where we see the smallest p-values. Notice their test statistics are in the tails of the distribution. They're further away from the center. That's something that is unexpected. We wouldn't expect to see the coin toss or 20 coin tosses result in that few heads. And then the next set, these p-values down here, these last 6 are fairly large. So we're not witnessing something extreme. These are outcomes that would be very likely to happen if our coin is fair. All right, so number 2, what do we do if it's not possible to collect a random sample? So medical researchers often cannot collect a random sample of people with a particular medical condition that they wish to study. They instead must rely on recruiting patients who come into hospitals. This type of convenient sample can be problematic for the statistical techniques we just learned. So sometimes we have to assume that the sample is random and/or representative of the population, and then use caution when interpreting the results. The medical study is a randomized controlled experiment, then the researchers may conclude that the treatment is effective for those people in their study, and then others may try to replicate the results with further studies. Number 3, what are the 2 types of mistakes or errors that can be made, and how do we balance these? So mistake number 1, we might reject the null hypothesis even though it's true. So the probability of this happening is indicated by the significance level. The smaller we set this probability, the higher the probability of making the other mistake, mistake number 2. So remember, the significance level is denoted by alpha. So mistake number 2, we fail to reject the null hypothesis when it's actually wrong. So which mistake is worse? Well, it depends on the study. So we're going to take a closer look at these types of mistakes in number 4. So for each of the following, state the null and alternative hypotheses, and then describe each of the 2 possible mistakes. And think about what would happen if we use a significance level of 0. All right, so in the example 1, person suspects the die used at a casino is biased. She decides to test this by rolling the die 100 times and recording the number of 6s. So the null hypothesis is that the proportion of rolls that end up in a 6 should be 1/6. It's another way of saying the die is fair. And our alternative is that the die is not fair. Then we end up with something other than 1/6 of our rolls being 6s. So again, in words, the die is unfair or not fair. All right, so mistake number 1 would mean that we conclude the die is not fair when it actually is. Okay, mistake number 2, we conclude the die is fair when it actually is not fair. Okay, so again, mistake number 2, we conclude the die is fair when it actually is not fair. So those are 2 types of mistakes. So think about what would happen if we set our significance level to 0. What that means is we would conclude that all dice are fair, whether they actually are or not. Okay, so example number 2, person is on trial for a specific crime. The prosecutor collects evidence for the case. So my null and alternative hypothesis here, I'm not going to use any symbols, but we're going to say that the null is the person is innocent. And in the alternative hypothesis, we're going to say the person is not innocent or is guilty. Okay, so our 2 types of mistakes. Mistake number 1, we conclude the person is guilty when he or she is innocent. And mistake number 2, we conclude the person is innocent when they are guilty. Okay, so this might be a good one to think about which mistake is worse. So again, mistake number 1, we conclude the person is guilty when they are innocent. So we're sending an innocent person to prison, perhaps. Mistake number 2, we conclude the person is innocent when they are actually guilty. So we're letting someone that has committed a crime go free. And so again, the question is, which mistake is worse? Depends on maybe the crime and personal opinion as well. So if you think about that last piece, what would happen if our significance level was 0? This would mean that everybody is found innocent. The amount of evidence you require to convict someone is too much. You're never going to get there. So you find everybody is innocent. And then our last one, example number 3, a new medical procedure is being tested in the fight against lung cancer. The doctor suspects that this medical procedure will help improve survival rates. All right, so our null hypothesis is that P is equal to the survival rate. And since we weren't given that, we'll just use words. And our alternative is that P is going to be greater. So our survival rate increases. So we'll put an extra word in here. We'll say it's greater than the current survival rate. And then our null hypothesis will say that it is the current, stays the same as the current survival rate. All right, so our two possible mistakes. First one, we would conclude that the medical procedure works when it really doesn't. And the second one, we conclude the procedure doesn't work when it really does. All right, so again, mistake number one, we conclude the medical procedure works and it really doesn't. In other words, the current survival rate stays the same. And let's see. Excuse me. So mistake number one, we conclude the medical procedure works when it really doesn't. So we're saying that a survival rate increased and it actually didn't. And mistake number two, we conclude the procedure doesn't work when it really does. All right, so think about what would happen if alpha were 0. In this case, no medical procedures work. We would never get enough evidence to say that a medical procedure worked. Okay, so number 5, statistically significant findings do not necessarily mean that the results are useful. Statistically significant results tell us that our sample results are so extreme when compared to what we expect to happen if the null hypothesis is true, that it cannot be convincingly explained by chance. And number 6, keep in mind that when you state your conclusion to a hypothesis test, you are not proving that the population proportion P is or is not equal to a particular value. If something is proved, then it is absolutely and without any doubt true. However, we cannot be absolutely certain about our results since they come from a random sample, and estimates from a random sample are uncertain. This is why we limit ourselves to one of the following conclusions. And our two choices are that we reject the null hypothesis or we don't reject the null hypothesis. So we're choosing the conclusion that seems most likely given our sample data. Instead of saying proved, use words like demonstrated or showed. And number 7, let's revisit the first hypothesis we did about whether or not a die was fair. So let's say I rolled the die 60 times and recorded 50 sixes. The following are the results of a confidence interval and a hypothesis done in StatCrunch. So just a quick reminder, that initial hypothesis we did, our null hypothesis said that P was 1/6. 1/6 of our rolls should be sixes. And our alternative hypothesis was that P was not 1/6. And in this case, I recorded 56s the next time I did it. So I got a P hat of 50 out of 60. Right. So looking at these results from StatCrunch, first thing I want you to notice is we've got our count here, 50 out of 60. Gives you P hat right there. Gives you the standard error, so you can confirm this if you'd like. And then it gives us the upper and lower limits of our confidence interval. So our confidence interval goes from here to here. So that confidence interval is giving us some plausible values of the proportion of sixes we could expect from this die. And the hypothesis test results, which are also from StatCrunch, so notice that the null hypothesis and the alternative hypothesis are right here. We did need to specify that it was two-tailed, that it wasn't equal to 1/6. And that's where this number is from. 1/6 in decimal form is the 0.166 repeating. We also had to tell it our sample results. So we got 50 out of 60 rolls being sixes. So it again gives us a P hat. Then gives us the standard error. But this time it's giving us our test statistic. So it's telling us how far away our P hat is from what we would have expected if the die was fair. So how far away from the hypothesized value it is, divided by our standard error. And then it's also giving us the p-value. And this would be 2 times the chance that we get a p-value, or that we get a test statistic this extreme. We get a test statistic more extreme than 13.86. And I'm just rounding this value to 2 decimal places. And so how are these results related? And we'll note up here in the confidence interval that this does not contain P equal to 1/6. And if you look at the hypothesis test results, you find that this p-value is so small that we would probably reject the null hypothesis. And that means that we would have enough evidence to support the alternative hypothesis that P was not 1/6. Right, so our confidence interval is saying that pi, or proportion P, equal to 1/6 is not a plausible value. And our hypothesis test is saying we should conclude that it's not 1/6. So confidence intervals in a hypothesis test, if it's a two-sided alternative hypothesis, they're actually closely related. So confidence interval provides a range of plausible values for your P, your population proportion. Should not be surprised if P turns out to be one of the values in the confidence interval. You would be surprised if it isn't. So keep in mind it uses a different standard error for both. There are rare cases where you could reach different conclusions. So let's take a look at the different standard error. So up here for your confidence interval, remember that this standard error gets calculated by taking the square root of P hat times 1 minus P hat over your sample size n. So in this case, our P hat was 50 out of 60. So times 1 minus 50 over 60. And our sample size was 60. And here our standard error is calculated using the null hypothesized value. So in this case, we hypothesized that P was 1/6. We're multiplying that times 1 minus 1/6 over the sample size. And that sample size in this case, I'm going to replace that with the actual number 60. Turns out they end up being the same value in this case. If you take a closer look at this up here, 50 out of 60 actually simplifies to 5/6, which is what this value is. And 1 minus 50 over 60 simplifies to 1/6. So in this case, we did get the same standard error, but note that they can be different in other situations. So in some cases, the results of the confidence interval could, and again, it's rare, give you something different than what the hypothesis test suggests. All right, so last thing here, remember that confidence intervals are used to answer the question, what is the value of the parameter? And a hypothesis test is used to answer the question, are the data consistent with the parameter being one particular value, or might the parameter be something else?